So, let's see. The chapter 5 quiz is due on the 8th. Sorry, the chapter 5 homework is due on the 8th. The chapter 5 quiz will also be on the 8th. It's moved from the 6th. So we have a slightly older schedule. I moved it. The chapter 6 homework will be on the 15th, is due on the 15th. The chapter 4 quiz grades are up, but I'm not handing them back today because there's still a decent number of people who need to make it up. I'm running a little behind on grading, so the grades for the tests will be up soon. So far, in general, people have done pretty well. So we'll see. Oh, things work better when you turn them on. So we're starting chapter 6, which is about waves. So we know that when matter is disturbed, energy emanates from that disturbance. You're experiencing that effect right now. I am disturbing matter with my throat and mouth, and that energy is emanating out about the room, and you're hearing it. This propagation of energy from this disturbance is known as a wave. The easiest sort of wave to see and visualize is a wave on water. You disturb the surface of water, you see a wave travel along the surface of the water. And this transfer of energy is called wave motion. So some examples are ocean waves, sound waves, electromagnetic waves, and seismic earthquake waves. There are other waves as well. There's lots of waves out there. So waves transfer energy and generally do not transfer matter through a variety of mediums. The waveform, the disturbance, moves through the medium, but the material of the medium itself doesn't particularly move. So water waves, for example, essentially bob you up and down. They don't really move you sideways. Earthquakes move through the earth, but they don't carry with them big chunks of earth. And sound waves travel through the air, but the air just moves back and forth. It doesn't travel any significant distance. And electromagnetic radiation waves travel through space. They can travel through the void. So any sort of disturbance, a disturbance could be a single pulse or shock, or it could be periodic, like a guitar string, or oh, that's a periodic wave coming from my vocal cords. So you could have a single strike, and that can, a single sharp shock, a single pulse, or you could have a repeating pattern. Now, we can classify waves into two general types based on how the matter moves, how the medium moves when the wave passes through it. So you can either have a wave where the medium moves perpendicular to the direction the wave travels. So this is known as a longitudinal wave. Oh, no, sorry, this is known as a transverse wave. Let me start over. So there's two types of waves. Waves travel in a direction. You can classify the type of wave based on how the particles move relative to the direction the wave is moving. So sound waves are a longitudinal wave. That means the wave is traveling this way. The particles move back and forth in the direction the wave is traveling. That's a longitudinal wave. It compresses and stretches the medium. So sound is a longitudinal wave like that. The other possibility is a transverse wave, where particle motion is perpendicular to the direction of the wave velocity. So that's like a wave on a string. The particles move up and down, the wave moves that way. So light is an example of something that is where the wave motion is perpendicular to the direction of wave velocity. And in general, you can classify waves as either transverse or longitudinal. There are a few exceptions out there that are sort of a mixture, but generally waves either move you perpendicular to the direction of motion of the wave or back and forth in the direction of motion of the wave. So a longitudinal wave compresses and stretches the medium. Here you can see it in a spring. So in a spring, you can have a longitudinal wave where you send a compression wave down along the direction of motion. You can also have, like what you have on a string, the particle moves up and down perpendicular to the direction of motion. That's a transverse wave. So sound is a longitudinal wave. It's a pressure wave. Light is a transverse wave. The electric and magnetic fields that make up light are perpendicular to the direction of motion of the light. So, you know, oh, no, it's not. So here I have this laser. If I'm pointing the laser that way, the electric magnetic fields are moving up and down and right and left. Or, you know, forward and back from your point of view. They're at right angles to the direction of the wave. So this is a transverse wave. So these are longitudinal.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
Because they compress and stretch.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
So this is a transverse wave. You can see the movement of the particles is up and down, while the wave is moving to your right. So they're at right angles. And here's a longitudinal wave, like a sound wave. The particles are moving left and right, and the wave is moving to the right. That's the difference. So a transverse wave is like a wave on a string. And a sound, you know, in a longitudinal wave, the particles are moving in the same, along the same direction as the wave is. In a transverse, they're perpendicular to it. So any wave can be described with a few properties. All waves have a wavelength. How long it takes for, you know, if you have a repeating wave, the distance to do one complete wave is the wavelength. The size from the rest state is the amplitude. So for sound, the wavelength is still, you know, how far it is to do one complete cycle. The amplitude would be, you know, how much the pressure increases or how much the density increases. The maximum displacement of any part of the wave from its equilibrium position. And the energy transmitted by a wave is directly proportional to the amplitude squared. So if you double the amplitude, you quadruple the energy. And then the wave will move along at some velocity. Additionally, because we have this repeating pattern that's passing by, well, that happens with some frequency. Every second, so many waves pass by. That is the frequency. So it's the number of oscillations or cycles that occur during a certain time. a second. And the unit we use to describe this is the hertz. Hertz is 1 cycle per second. So something that is 5 hertz is going to do 5 cycles every second. Something that's 5,000 hertz is going to do 5,000 cycles every second. And something that's, 5 gigahertz is going to do 5 billion cycles every second. And then period. The period is the time it takes for one wavelength or one cycle of a wave to occur. So it's just 1 over the frequency. So frequency and period are inversely proportional. Frequency is 1 over period. Period is 1 over frequency. So frequency is in cycles per second. If a wave has a frequency of 4 hertz, then 4 full wavelengths will pass in 1 second. Therefore, 4 full wavelengths pass in 1 second. It takes a quarter second for each wavelength to pass. So the period is 1 over the frequency. It's 1/4 of a second. So the period is also the time it takes for one wavelength to pass you. So if 2 waves are traveling at the same speed, and you double the frequency, and one is double the frequency of the other, it will have half the wavelength. The wavelength and frequency are related to speed. So here we have 2 waves with the same velocity and different wavelengths. And you can see that the longer wavelength wave has a lower frequency. It does less cycles per second, while the shorter wavelength wave has a higher frequency. It does more cycles per second. So as long as they have the same velocity, frequency and wavelength are inversely related in their way. So if a water wave has a period of half a second, 0.5 seconds, what is its frequency? So remember, frequency is 1 over period, or period is 1 over. 2 hertz.
Yeah.
So 1 over 0.5 seconds is 2 hertz. Hertz is actually the same as inverse seconds, 1 over seconds. But 2 hertz. So if a sound wave has a frequency of 10 kilohertz, what is its period? You forgot to convert, because that's kilohertz. That's 10,000 hertz. The frequency is 1 over period. Period is 1 over frequency. So 1 over 10 kilohertz is 1 over 10,000 hertz, which is 0.0001 seconds. 1/10,000. And that's going to be important because a lot of things are going to be in kilohertz or gigahertz. Now, just for example, sound that is audible to humans goes from about 20 hertz to about 20 kilohertz. And light, we don't even talk about light unless it's at least in the kilohertz range. That's the long wavelength stuff for light. Short wavelength stuff, we have to press with, or 0.1 milliseconds. So speed is distance over time. And in one period, you will travel one wavelength. Your wave will travel one wavelength. So your speed is going to be your wavelengths divided by your period. But 1 over the period is the frequency. Okay? So your speed is wavelength times frequency. And generally, for waves, the speed does not depend very strongly on the wavelength of the frequency. I'm not going to say it doesn't depend on it, because there are effects that are based on that. But usually, the speed doesn't particularly depend on it. And that means, if you know the speed, frequency is going to be speed over wavelength, or wavelength is going to be speed over frequency. So speed, speed, wavelength, times frequency. So frequency is wavelength, sorry, speed over wavelength, and wavelength is speed over frequency. So here we have 2 waves with the same frequency but different velocities. Here we have a fast wave with the same frequency. You can see the wavelength is longer. And here we have a wave, same is a slower wave, same frequency. You can see these red speaker things are moving back and forth at the same speed. But because the velocity is lower, it's a shorter wavelength. And this effect where you get it, well, actually, it's sort of the other way around. But this relationship between speed, wavelength, and frequency is part of why when you breathe helium, your voice sounds so high-pitched. Because your voice is, it turns out what's determined for your voice is the wavelength from like the structure of the inside of your throat. And when you increase the speed of sound by replacing air with helium, you increase the frequency, and what we hear is the frequency. So here's an example of calculating wavelengths. So let's say we have sound waves with a speed of 344 meters per second. That's, I mean, the speed of sound depends on the temperature, but that's the speed of sound around room temperature. And frequencies of 20 hertz and 20 kilohertz. What will the wavelengths of these individual sound waves be? So 20 hertz is about the bottom of human hearing, 20 kilohertz is the top of human hearing. It's above the top of my hearing. I'm older. So given that the speed is 344 meters per second, the frequency is 20 hertz or 20 kilohertz, which is 20,000 hertz. We want to find the wavelength. So wavelength is velocity divided by frequency. So 344 meters per second divided by 20 hertz gives us 17 meters. And so the bottom of human hearing is a wave around 17 meters long. And at the top of human hearing, 344 meters per second divided by 20 kilohertz is about it's 0.017 meters, or about 1.7 centimeters long. So if you have a sound wave with a speed of 344 meters per second and a wavelength of half a meter, what will the frequency of the wave be? So for this, frequency is speed over wavelength. So 344 meters per second divided by 0.5 meters gives us 688 cycles per second, or 688 hertz. So if you're out at sea and a water wave has a speed of 50 meters per second and a wavelength of 250 meters, what is the frequency of this wave? Sound wave. Frequency is going to be speed divided by wavelength. So 50 divided by 250, which is 0.2. Each wave will come as a period of 5 seconds. So here we have a wave that has a wavelength of 2,000 meters and a frequency of 150 kilohertz. What is its speed? So speed is frequency times wavelength. So it's going to be 2,000 meters times 150 kilohertz. So that's 2,000 meters times 150,000 hertz. So 150 kilohertz times 2,000 meters, that's 150,000 hertz times 2,000 meters. That is 300 million meters per second, which is the speed of light. That is a radio wave. So 3 times 10 to the 8th meters per second. So here we have the standard musical note, A above middle C. It has a frequency of 440 hertz. If the speed of sound is 334 meters per second, which is what it is at around freezing, what is the wavelength of this note? I think that's what it is around freezing. Look at those. Okay, it's a little above freezing. But this is when it's cold. At room temperature, it's around 340 or 44. But that's well in the normal range for sound. Depends. So, speed of sound is 334 meters per second. The frequency is 440 hertz. Speed is frequency times wavelength. So wavelength is speed divided by frequency. So 334 meters per second divided by 440 hertz gives you a wavelength of 0.759 meters. So A over middle C has a wavelength of 0.759 meters, which is why if you have a fluid that's a quarter of that length, it will produce that number.
Right.
We can go a little further. So we talk about the description of a wave. We talked about wave speed. Let's discuss electromagnetic waves. We talked a bit about sound. Now let's talk about electromagnetic waves. So electromagnetic waves consist of vibrating electric and magnetic fields that oscillate perpendicular to each other. So electromagnetic waves are longitudinal waves. They have a portion, the electric field goes one direction and the magnetic field goes at right angles to it. And the field energy radiates outwards at the speed of light. And the speed of light in a vacuum is 3 times 10 to the 8th meters per second, which is about 1.86 times 10 to the 5th miles per second. Or about a foot every nanosecond. So, and this is to a good approximation the speed of light in air. The difference is less than it is around a 0.1%. So it's a very small difference. It is a little bit slower in air. It's a little bit, light is slower in various mediums. That's why lenses work. This is the fact that light slows down when you go into glass to bend light. So here is an electromagnetic wave. It has an electric field that is changing, which creates a magnetic field, which is changing. And because the magnetic field is changing, it creates an electric field and back and forth. This is how it doesn't need to pass through anything. The electric field creates the magnetic field creates the electric field. The whole thing is just in the electromagnetic field. And so can travel through absolutely empty space. And both the electric and magnetic fields are perpendicular to the direction that the wave travels. And because this is a longitudinal wave, it has some things like it can be polarized, things like that, which we'll get to later. So electromagnetic waves cover a huge range. You can talk about electromagnetic waves of basically any frequency. Electromagnetic waves that we deal with as humans vary from things like 10 to the 20 hertz at the high energy, high frequency, short wavelength end. That's things like gamma rays. And then at the long wavelength end, low frequency, we go down to 10 to the 4, maybe as low as, below around 10,000 hertz. We don't really use those. They're just not so useful. But down in the radio waves. Now, we as humans see a tiny portion of this. We see from 7.5 times 10 to the 14 hertz to 4.3 times 10 to the 14 hertz, which is 400 nanometers to 700 nanometers. 400 nanometers is like violet, 700 nanometers is red. Now there are some animals that see outside this, beyond this range, but that is the limited human vision. And so we call that section the visible light. So from the visible, if we go to shorter wavelengths, higher frequencies, we have ultraviolet, above violet. Higher frequency, it's above violet. Then above ultraviolet, we have the X-rays and then gamma rays. So, and these distinctions are more or less just arbitrary divisions where we've set the divided. When we go down to longer wavelength, lower frequency and lower energy, we have infrared below red, then we have microwaves, and then we have radio waves. Again, these distinctions are more or less arbitrary. So the electromagnetic spectrum is all the different types of light.
Hey, it's Professor Dave. Let's learn about light.
He knows a lot about the science stuff. Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So here's an example of that calculation where we would compute the wavelength of the radio waves produced by a station with a frequency of 600 kilohertz. So 600 kilohertz is 600 times 10 to the third hertz, or 6 times 10 to the 5 hertz. Speed of light equals wavelength times frequency. So wavelength equals speed of light divided by frequency. So 3 times 10 to the 8th meters per second divided by 6 times 10 to the 5th hertz gives us a wavelength of 0.5 times 10 to the 3rd meters, or 500 meters. So I think that's where I'm going to stop for today, and then we can get started on the lab. I'm going to end the